concept on the realization of harmonic frequency comps in the project T-Next. Optical frequency comps are light sources whose emission spectrum is characterized by evenly spaced optical modes. In a terahertz range, this can be realized by quantum cascade lasers, which are semiconductor-based terahertz sources. By including defects on the top contact of these terahertz cavities, we can obtain harmonic frequency comps, which, differently from standard comps, include a lower number of modes. Therefore, the total laser power is shared among less modes, which are therefore more intense. Here we can see some images of our quantum cascade lasers. We can see images obtained with scanning electron micrograph and image taken at the optical microscope. As we see, the number of modes can be changed in order to decide the output spectrum of the quantum cascade laser. In this slide, we see the difference in the output spectra of a standard quantum cascade laser in the top and of harmonic frequency comps below. As we see, a lower number of modes is active. The harmonic frequency comps can be used together with the diffraction gratings to separate the optical modes and send each mode to a different photodetector. This strategy could, for example, be used in free space optical communication in the terahertz range. So this is the terahertz photonics lab, and this is the instrumentation we use to characterize terahertz quantum cascade laser. This is a Fourier transform infrared spectrometer that works in vacuum to remove the atmospheric absorption. And here, on top of the spectrometer, we can see some samples of quantum cascade laser devices. Since terahertz quantum cascade laser do not operate at room temperature, we use this helium flow cryostat to operate the QCL from helium temperature, which is 4 Kelvin, up to room temperature.
In order to improve the performance of graphene-based terahertz detectors, we integrate a graphene terafed onto a photonic platform. In this architecture, an antenna-coupled photodetector is placed on the terahertz cavity, which is designed to maximize the field in the center of the antenna. This is based on a Salisbury screen geometry, which relies on a dielectric spacer whose thickness is designed to enhance the light on the graphene active element. Here we see the different elements composing the photodetector. A gold back reflector is covered by a polyimide spacer, and on top of the spacer, the antenna-coupled graphene photodetector is fabricated, obtaining this antenna-coupled graphene Salisbury screen. This is the experimental setup that we use to perform both electrical and optical characterization of our photodetectors. It is based on a terahertz quantum cascade laser enclosed in this Stirling cryostat. The light of the laser is focused on the detector. The precise motion of the detector position allows us to maximize the signal and reconstruct the beam shape in the focal plane.
In this video, we present the setups for the testing of the silicon-based terahertz receiver designed in the Department of Information Engineering, Electronics and Telecommunications of Sapienza University of Rome, and currently under fabrication. Our purpose is to characterize a silicon-based terahertz receiver by setting up a wireless transmission chain in on-off keying at 100 megabits per second at 700 gigahertz carrier frequency. To generate a 3 gigahertz signal modulated in on-off keying, we used a Rode and Schwarz radio frequency signal generator, driven by an external square pulse generator, to perform an amplitude modulation at 100% modulation depth of the carrier. Then, we use a frequency multiplication stage to achieve a signal at 12 gigahertz. The 12 gigahertz amplification stage is necessary to achieve the required output power level to be fed to the subsequent terahertz upconversion stage. In the alternative approach, we used an Anritsu digital signal quality analyzer equipped with a pulse pattern generator to generate a pulse pattern at 12 gigahertz. Our characterization setup include an Anritsu digital signal analyzer and pulse pattern generator, a Teledyne oscilloscope, and a Keysight spectrum analyzer. The 12 gigahertz signal is fed as input signal to the terahertz frequency upconversion device. The output terahertz wireless signal is focused by 2 terahertz lenses on the microbolometric camera. We use a micro-XCAM-uncooled microbolometric detector and a Thorlabs terahertz 2-lens system. This picture shows the complete characterization setup, from signal generation to terahertz camera detection. The terahertz signal is detected and processed as a light spot image. So, by processing the microbolometric camera images, we assess the quality of the terahertz signal by measuring the linear dependence of the received power as a function of the on-off keying pulse's duty cycle.